Listening practice, forward the imperative of seismic resilience, bridging academia and industry. Earthquakes are not merely natural phenomena, they are social, economic, and human tragedies waiting to unfold. Over the past century, seismic disasters from Kobe to Kathmandu, Christchurch to Karamanmaras, have exposed the devastating consequences of unprepared infrastructure and fragmented knowledge systems. Yet, amid these tragedies, we have witnessed extraordinary resilience, engineers retrofitting centuries-old monuments, communities rebuilding with newfound wisdom, and technologies emerging to predict the unpredictable. This book is born from the urgent need to bridge the gap between academic research and real-world practice. While seismic engineering principles are well documented in theory, their translation into industry-ready solutions remains fraught with challenges: outdated codes, skill shortages, and a lack of collaboration between policymakers and practitioners. The 2023 earthquakes in Turkey, for instance, underscored the catastrophic cost of ignoring these divides. Earthquake-resistant structures, design, analysis, and innovations * is not just a technical manual, it is a call to action. By weaving together cutting-edge research, global case studies, and actionable workforce strategies, this book empowers engineers, architects, and planners to transform theory into life-saving practice. It challenges academia to align curricula with industry demands and urges policymakers to invest in training programs that turn seismic resilience from an aspiration into a universal standard. The path to resilience is neither simple nor solitary. It requires engineers who understand sociology, policymakers fluent in material science, and communities trained to demand safer infrastructure. This book is a blueprint for that collaborative future, one where innovation is democratized, knowledge is shared, and no community is left vulnerable. Dr. Hiroshi Tanaka, Chair, International Association for Earthquake Engineering. Preface. Scope and objectives: integrating industry-ready skills with engineering theory. This book began as an exploration of seismic design principles but evolved into something far more ambitious, a holistic guide to building not just earthquake-resistant structures, but earthquake-resilient societies. Scope: the text spans 5 core pillars: 1. Foundational theory, ground motion dynamics, structural behavior, and code-based design. 2. Practical application, retrofitting techniques, material innovations, and compliance frameworks. 3. Global case studies, lessons from high-risk regions like Japan, New Zealand, and Turkey. 4. Policy and workforce development, strategies to upskill engineers and align regulations with technological advances. 5. Future-ready tools, AI, quantum computing, and bio-inspired design reshaping the field. New to this edition, responding to feedback from educators and industry leaders, this edition introduces Part 4, Industry Training and Workforce Development, addressing critical gaps in professional seismic engineering, certifications and licensing, navigating credentials like the Structural Engineering Certification Board, SECB, exams. Digital upskilling, using VR simulations for hazard scenarios and AI tools for real-time risk assessments. Global equity, tailoring training programs for developing nations, where 90% of earthquake fatalities occur. Objectives: 1. For students, demystify seismic design with code examples, MATLAB/Python scripts, and hands-on retrofitting exercises. 2. For practitioners, provide checklists for ASCE 41 compliance, tax incentive guides, and templates for community engagement. 3. For policymakers, highlight cost-benefit analyses of retrofitting programs and models for public-private training partnerships. Audience: engineers and architects, master performance-based design and emerging materials like shape memory alloys. Educators: integrate modular coursework on seismic isolation or climate-induced seismicity. Policymakers: leverage case studies from Mexico's. Here's the finalized Part I, Fundamentals of Earthquake Engineering, maintained as originally structured but contextualized to align with the book's expanded focus on industry training and workforce development. Part I, Fundamentals of Earthquake Engineering 1. Introduction to Seismic Hazards, 1.1 Seismology Basics, Plate Tectonics and Fault Mechanisms, 1.2 Ground Motion Characteristics, PGA, Spectral Acceleration and Duration, 1.3 Seismic Risk Assessment, Probabilistic versus Deterministic Approaches to Structural Dynamics and Earthquake Loads, 2.1 Single Degree of Freedom, SDOF, Systems, 2.2 Multi-Degree of Freedom, MDOF, Systems, 2.3 Response Spectrum Analysis and Design Spectra 3. Performance-Based Earthquake Engineering, 3.1 Performance Objectives, Immediate Occupancy to Collapse Prevention, 3.2 Ductility and Energy Dissipation Concepts, 3.3 Fragility Curves and Risk Mitigation - Integration with Industry Training. While Part I focuses on foundational theory, key concepts are later applied in Part 4, Industry Training and Workforce Development, Chapter 15, Certification Exams, e.g., ASCE exam, Test Competency in Spectral Analysis and Code-Based Design. Chapter 17, VR Simulations in Training Modules use SDOF/MDOF models to teach dynamic response. Case Studies, Performance Objectives, CH 3.1, are linked to real-world retrofitting projects in Turkey and New Zealand, Part B. This foundational knowledge ensures readers grasp the science behind seismic forces before advancing to practical implementation and workforce strategies. Let me know if you'd like to refine other sections. Here's the finalized Part 2, Seismic Design Principles, maintained as originally structured but contextualized to align with the book's expanded focus on workforce training and practical implementation. Part 2, Seismic Design Principles 4. Design Codes and Standards, 4.1 International Codes, ASCE 7, Eurocode 8, and IS 1893 to 4.2 Load Combinations and Seismic Force Calculations, 4.3 Importance Factors and Occupancy Categories 5. Reinforced Concrete Structures, 5.1 Ductile Detailing, Beam Column Joints, Confinement and Lap Splices, 5.2 Shear Walls and Moment Resisting Frames, 5.3 Case Study, Chile's 2010 Earthquake and Post-Tensioned Buildings 6. Steel Structures, 6.1 Concentrically and eccentrically braced frames, 6.2 Moment Resisting Connections and Reduced Beam Sections, 6.3 Case Study, Japan Steel Skyscrapers and the 2011 Tohoku Earthquake 7. Masonry and Timber Structures, 7.1 Reinforced Masonry, Horizontal and Vertical Reinforcement, 7.2 Cross-Laminated Timber, CLT, and Resilient Joints, 7.3 Retrofitting Historic Masonry Buildings - Integration with Industry Training. The principles in Part 2 are directly tied to Part 4, Industry Training and Workforce Development, Certification Alignment, Chapter 4's Code-Based Design, e.g., ASCE 7 Load Combinations, is foundational for licensure exams like the ASCE Structural Engineering, ASCE, exam. Hands-on workshops, Reinforced Concrete, CH5 training modules on ductile detailing and post-tensioning, inspired by Chile's case study, are used in workshops like California's Peer Center programs, Steel Structures, CH6 VR Simulations, CH17.1, Train Engineers on Moment-Resisting Connections, Mirroring Japan's Skyscraper Resilience, Retrofitting Skills, Masonry Retrofitting Techniques, CH7.3, are taught in Nepal's NSET-led Community Mason programs, CH12.2, Compliance Tools, Checklists in Appendix C, ASCE 41, FEMA P58, Guide Professionals in Applying Code Requirements to Real Projects. This section ensures readers not only grasp design theory but also learn how these principles are applied in industry settings, from code enforcement to material-specific construction best practices. Let me know if you'd like to refine the integration points or add specific examples. Here's the finalized Part 3, Advanced Materials and Innovative Systems, contextualized to align with the book's focus on workforce training, global case studies, and practical implementation. Part 3, Advanced Materials and Innovative Systems 8. Base isolation and energy dissipation devices, 8.1 elastomeric and lead rubber bearings, design principles and installation protocols, 8.2 viscous dampers and tuned mass dampers, applications in high-rise and critical infrastructure, 8.3 case study, San Francisco City Hall retrofit balancing heritage preservation with seismic safety 9. Seismic retrofitting techniques, 9.1 FRP, fiber reinforced polymer, wrapping, strengthening bridges and columns, 9.2 jacketing and supplemental damping, cost-effective solutions for aging infrastructure, 9.3 retrofitting soft story buildings, lessons from the 1994 Northridge earthquake 10. Emerging technologies, 10.1 self-centering structures with shape memory alloys, SMAs reducing residual deformations in skyscrapers, 10.2 3D printed earthquake-resistant components, custom lattice structures and topology optimization, 10.3 AI-driven seismic risk prediction, real-time monitoring and adaptive design - integration with industry training 1. Certification alignment, CH15, base isolation, CH8 engineers pursuing EERI certifications must demonstrate proficiency in selecting and installing isolation systems, FRP retrofitting, CH 9.1 hands-on workshops, CH 16.1, train masons in fiber-reinforced polymer applications, as seen in Nepal's NSET programs. 2. Digital upskilling, CH 17, AI-driven risk prediction, CH 10.3 online modules, e.g., FEMA's EMI, teach engineers to integrate AI tools like OpenQuake into hazard assessments, 3D printing, CH 10.2 VR simulations model layer-by-layer printing of seismic-resistant components, reducing material waste in training. 3. Global case studies, Part V, San Francisco City Hall retrofit, CH 8.3 used in workshops to demonstrate compliance with FEMA 547 guidelines for historic structures, Northridge retrofits, CH 9.3 lessons inform California's earthquake brace and bold program, training contractors in soft story mitigation. 4. Sustainability and equity, shape memory alloys, CH 10.1 highlighted in UN Sendai framework training for their potential to reduce life cycle costs in low-income regions. 3D printing, case studies like Zurich's concrete columns emphasize eco-friendly designs, aligning with green certification standards. Key innovations, self-healing materials, bio-inspired concrete with calcifying bacteria, linked to CH 14.2, is tested in Japan's coastal infrastructure. Hybrid systems, combining base isolation with SMA dampers for multi-hazard resilience, e.g., seismic and tsunami forces. Challenges, cost barriers, high initial costs of SMAs and 3D printing require subsidies, CH 13.2, and workforce training to scale adoption. Regulatory gaps, building codes lag behind material innovations, upskilling code officials is critical, CH 16.2. This section bridges cutting-edge technologies with actionable training strategies, preparing engineers to implement innovations like AI and 3D printing while addressing cost, regulatory, and sustainability challenges. Let me know if you'd like to expand on specific case studies or tools. Part 4, Industry Training and Workforce Development 15. Professional Certification and Skill Building 15.1 Seismic Engineering Certifications, CAIC, EERI, ICC, certifications validate expertise and ensure adherence to safety standards in seismic design. Key programs include, CAIC, Structural Engineers Association of California, certifications, offers the CAIC Seismic Design Manual endorsement for engineers specializing in California's stringent codes. Requirements, minimum 5 years of experience, peer review of seismic projects, and ongoing CEUs, continuing education units. EERI, Earthquake Engineering Research Institute, certifications, focuses on research and practical application, with credentials like the Seismic Risk Assessment Specialist. Benefits, grants access to global networks and disaster reconnaissance missions, e.g., Post-Turkey 2023 earthquakes. ICC, International Code Council, certifications, ICC Structural Engineering Certification for Code Compliance in Seismic Zones. Case study, Los Angeles mandates ICC certified engineers for public infrastructure retrofits. 15.2 Accreditation bodies, role of NSAs and national licensing boards. These organizations standardize qualifications and ensure public safety. NSAs, National Council of Examiners for Engineering and Surveying, exams, administers the structural engineering, ASCE, exam, covering seismic load calculations and code adherence. Licensing, required in 35 U.S. states for practicing structural engineers. National licensing boards, examples, California's POLSC, Board for Professional Engineers, Land Surveyors, and Geologists, enforces seismic design competency. Global parallel, Japan's Building Officials Institute certifies engineers for high-rise construction in Tokyo's seismic zones. Challenges, rural regions often lack access to testing centers, prompting online proctoring initiatives. 15.3 Competency frameworks for seismic design professionals. Frameworks define skills needed to address modern seismic challenges, core competencies, technical, nonlinear dynamic analysis, retrofitting techniques, e.g., FRP wrapping, and AI-driven risk modeling. Soft skills, community engagement for resilience planning and interdisciplinary collaboration. Implementation, FEMA's competency model, outlines tiers from entry-level code compliance to advanced performance-based design. Global examples, Nepal's NSET trains masons in seismic-resistant masonry, aligning with UN Sustainable Development Goals. Case study, Chile's post-2010 reforms, mandated competency in base isolation design for engineers working on public hospitals. Integration with workforce development, certifications and competencies. EERI's training programs integrate FEMA's frameworks, ensuring engineers meet both technical and community-focused standards. Policy alignment, California's SB 1953 requires hospital retrofit designs to be reviewed by NSA's licensed engineers, bridging policy and practice. Equity initiatives, ICC offers subsidized exams in developing nations, addressing skill gaps in earthquake-prone regions like Haiti. Challenges and solutions, cost barriers, CAX scholarship program for underrepresented engineers. Technological gaps, FEMA's ME online courses provide free training on ASCE 41 compliance. Conclusion. Professional certifications, rigorous accreditation, and competency frameworks form the backbone of a resilient workforce. By aligning with global standards like the UN Sendai framework, these tools empower engineers to transform seismic theory into life-saving practice, ensuring structures withstand both current and future hazards. 16 Industry-academia collaboration. 16.1 Internship programs, bridging classroom learning and field practice. Internships are critical for translating theoretical knowledge into practical skills, fostering a workforce adept at addressing real-world seismic challenges. Key features include, structured partnerships, university-industry alliances. Programs like MIT's NEAS Consortium pair students with firms specializing in seismic retrofitting and code compliance. Government collaborations, the USGS Earthquake Science Center offers internships focused on hazard mapping and sensor network management. Skill development, hands-on training, interns conduct nonlinear dynamic analyses, retrofit soft story buildings, and engage in community risk assessments. Mentorship, senior engineers guide interns in applying ASCE 7 load combinations or FEMA P58 performance assessments. Challenges, equity gaps, rural or low-income students often lack access to urban-based programs. Solutions, virtual internships, e.g., remote seismic monitoring projects, and stipends for underrepresented groups. Example, UC Berkeley's peer internship program. Students work on live projects like San Francisco's Transbay Terminal retrofit, gaining experience in base isolation design and stakeholder coordination. 16.2 Continuing education, workshops, webinars, and short courses. Lifelong learning ensures professionals stay current with evolving codes, materials, and technologies. Workshops, ASCE seismic retrofit workshops, hands-on sessions on FRP wrapping and shear wall design, aligned with ASCE 41 standards. EERI's reconnaissance training, prepares engineers for post-disaster data collection, e.g., 2023 Turkey earthquake damage assessments. Webinars, FEMA's Emmy series, covers topics like HAZIS risk modeling and AI-driven fragility curve development. NIST seismic tools for practitioners, free modules on performance-based design for federal projects. Short courses, Stanford's Advanced Seismic Isolation, trains engineers in lead rubber bearing installations and maintenance. Global initiatives, Nepal's NSET offers masonry retrofitting courses for rural builders, integrating traditional techniques with modern codes. Credits and certification, programs often grant CEUs, continuing education units, or digital badges, e.g., EERI Seismic Risk Management Badge. 16.3 Case Study, California's Peer Center Training Initiatives. The Pacific Earthquake Engineering Research, Peer Center exemplifies academia-industry synergy through key programs. Next Generation Performance-Based Design, trains engineers in AI-aided nonlinear analysis tools, bridging research, e.g., OpenSea software and practice. Retrofitting Workforce Pipeline, partners with community colleges to certify technicians in FRP and steel jacketing. Impact, Policy Influence, Peers research on soft-story buildings informed California's mandatory retrofit ordinance, SB 585. Global reach, peer-trained engineers led base isolation designs for hospitals in Chile and Indonesia. Challenges and solutions, funding volatility, addressed through public-private partnerships, e.g., PG&E grants for wildfire seismic risk workshops. Knowledge transfer, Peers open access webinars democratize advanced tools for global practitioners. Outcomes, over 5,000 professionals trained since 2010, with 85% reporting improved competency in performance-based design. Integration with workforce development, curriculum alignment, Peers workshops reference case studies from Part B, e.g., Christchurch Rebuild, to contextualize training. Digital tools, VR simulations, CH 17.1, model Peers retrofitting projects, allowing remote learners to practice beam column joint repairs. Equity, Peers stipend program for women and minorities mirrors Nepal's NSET gender inclusive training, CH 12.2. Global parallels, Japan's BRIQ initiative, combines university research, e.g., Tokyo Institute of Technology, with contractor training in tsunami-resistant design. New Zealand's Quake Core, industry-funded workshops on seismic isolation for heritage buildings, akin to Peers model. Conclusion, industry-academia collaboration transforms seismic resilience from theory to practice. By fostering internships, continuing education, and centers like Peer, the field cultivates a workforce capable of designing adaptive, equitable, and code-compliant infrastructure for earthquake-prone regions worldwide. 17 Digital tools for training. 17.1 Virtual reality, VR, simulations for earthquake scenarios. Definition and application, VR simulations immerse engineers in realistic earthquake scenarios, enabling them to visualize structural behavior, identify failure points, and test mitigation strategies in a risk-free environment. Tools like Oculus Rift or HTC Vive are paired with physics-based software, e.g., ANSYS Experience, to simulate seismic events. Benefits, hands-on learning, engineers practice retrofitting virtual buildings, e.g., soft-story structures, and observe real-time stress distribution. Cost-effective training, reduces need for physical prototypes, ideal for complex scenarios like tsunami-coupled earthquakes. Safety, eliminates risks associated with live disaster drills. Challenges, high costs, advanced VR hardware/software can be prohibitive for small firms or developing nations. Technical complexity requires expertise in both seismic engineering and VR development. Accuracy, simulations must align with real-world physics, e.g., ground motion models from Pier Na West 2. Examples: Stanford University's Virtual Disaster Lab trains engineers to assess post-earthquake damage using VR reconstructions of the 2010 Haiti earthquake. Europe's VR retrofit tool allows users to modify virtual buildings with base isolators or dampers and test performance under simulated tremors. 17.2 Online platforms, FEMA's EMI and NIST training modules. Definition and application. Online platforms provide scalable, standardized training for seismic resilience. FEMA's Emergency Management Institute, EMI, offers courses like IS 325, Earthquake Basics, and E190, HAGIS for Earthquake, focusing on risk assessment and community planning. NIST training modules, resources such as * seismic rehabilitation of buildings align with ASCE 41 standards, covering retrofitting techniques and material testing. Benefits: accessibility, free or low-cost courses, e.g., EMI's online library, democratize access to global audiences. Interactivity, quizzes and virtual labs, e.g., NIST Seismic Performance Assessment Tool, reinforce learning. Challenges: engagement, passive content delivery risks low completion rates, gamification can mitigate this. Currency, modules must regularly update to reflect new codes, e.g., FEMA P2091 for performance-based design. Examples: EMI's HAGIS training, used by planners in Chile to model economic losses for the 2023 Valparaiso earthquake scenario. NIST's retrofit guidelines, adopted by Nepal's NSET for training masons in earthquake-resistant masonry. 17.3 AI-driven competency assessments for engineers. Definition and application. AI evaluates engineers' skills through adaptive testing and scenario-based simulations. Platforms like Cogni use natural language processing to grade open response questions, while Boomerang Analytics assesses decision-making in virtual seismic design challenges. Benefits: personalized feedback, AI identifies knowledge gaps, e.g., misunderstanding ductility ratios, and recommends tailored resources. Scalability, automates grading for certifications like EERI's Seismic Risk Specialist, reducing administrative burdens. Challenges: bias risks, training datasets must reflect diverse seismic contexts, e.g., informal settlements versus high-rises. Data dependency, requires large datasets of expert responses to ensure accuracy. Examples: Pier's AI assessment tool, evaluates engineers' ability to optimize base isolators in simulated high-rise designs. FEMA's Competency Bot, guides users through virtual scenarios, e.g., post-earthquake inspections, and scores compliance with FEMA P58. Integration with workforce development, VR and internships. UC Berkeley interns use VR to simulate retrofitting projects before fieldwork, CH 16.1. Online courses and certifications, completing EMI's E190 counts toward ICC's structural engineering certification, CH 15.1. AI and equity. NIST's low-bandwidth AI tools provide competency assessments in regions with limited internet access. Global impact, VR in developing nations, partnerships, e.g., World Bank, fund VR labs in Indonesia to train engineers in tsunami-resistant design. AI for code compliance. Mexico's SASMEX system uses AI assessments to certify engineers in early warning integration. Conclusion: digital tools are revolutionizing seismic training, bridging gaps between theory and practice. By addressing challenges like cost and bias, these innovations empower a global workforce to build resilient, adaptive infrastructure. 18 Global Workforce Challenges. 18.1 Skill Gaps in Developing Nations. Nepal, Indonesia, and Haiti. Challenges: developing nations face systemic barriers to building a skilled seismic engineering workforce. Nepal, traditional practices, reliance on non-engineered masonry and adobe construction persists, despite revised 2020 building codes. Training gaps: only 15% of rural masons are trained in seismic-resistant techniques, e.g., vertical rebar in brick walls. Solutions: NSET Nepal's community mason programs have trained 50,000 plus builders since 2015, using vernacular materials like bamboo and wire mesh. Indonesia: geographic fragmentation, training programs struggle to reach 17,000 plus islands, where informal settlements dominate. Case study: the World Bank's Jakarta Urgent Flood Mitigation Project integrates seismic retrofitting into flood-resistant housing, training 2,000 local engineers. Haiti: legacy of disaster. The 2010 earthquake exposed a near-total lack of certified engineers, only 10 licensed structural engineers nationwide. Progress: NGOs like Build Change train locals in confined masonry, constructing 30,000 plus retrofitted homes since 2010. Key barriers: funding shortages for formal education programs. Brain drain as skilled engineers emigrate for opportunities. 18.2 Retaining talent in high-risk regions. Challenges: earthquake-prone regions often lose skilled professionals due to economic factors, low salaries in public sector roles, e.g., Nepal's government engineers earn $300/month. Limited career growth, few opportunities for specialization in advanced techniques like base isolation or AI-driven risk modeling. Psychosocial stress, trauma from recurrent disasters drives engineers to relocate. Solutions: incentive programs. Chile's Seismic Talent Fund offers grants for engineers working in high-risk zones like Valparaiso. Turkey's post-2023 reforms doubled salaries for engineers in earthquake-affected provinces. Professional development: New Zealand's Quake Corps funds research fellowships to retain experts in Christchurch. Remote work, allowing engineers in regions like Indonesia to collaborate globally on projects, e.g., open quake development. Community ties, engaging local engineers in culturally significant projects, such as retrofitting Haiti's iron market or Nepal's Bhaktapur temples. 18.3 Case study: Japan's Resilience Engineer Training Programs Overview. Japan's workforce strategy combines rigorous education, hands-on training, and national pride in disaster resilience. Education pipeline: university programs. Institutions like Kyoto University offer specialized M.Eng. tracks in seismic and tsunami engineering. Vocational schools train technicians in base isolation installation and dampers maintenance. Industry collaboration, public-private partnerships. Firms like Kojima Corporation sponsor internships focused on skyscraper damping systems. Licensing *, mandatory building disaster prevention advisor certification for engineers working on high-risk infrastructure. Continuous learning, resilience engineer workshops, annual drills simulating mega-earthquakes, e.g., Tokai/Tonankai scenarios. AI integration, training in AI tools like Terra Seismic for real-time fault monitoring. Impact: Japan retains 85% of its seismic engineering graduates domestically. Innovations like Tokyo's Yokohama Landmark Tower, equipped with hybrid dampers, emerged from this ecosystem. Global lessons, mentorship models, pairing junior engineers with disaster survivors to emphasize social impact. Policy alignment: Japan's Building Standards Act mandates continuous education credits for license renewal. Integration with workforce development, skill gaps and training. Nepal's NSET programs mirror Japan's vocational schools but adapt to low-resource contexts, e.g., using mobile training units. Talent retention and policy: Chile's incentive programs align with Japan's licensure mandates, emphasizing long-term career pathways. Technology transfer: Haiti's use of 3D printed seismic connectors, CH10.2, draws from Japanese prefab techniques. Conclusion: addressing global workforce challenges requires context-specific strategies from Nepal's community-centric training to Japan's high-tech pipelines. By investing in education, equitable incentives, and cross-border collaboration, the seismic engineering field can build a resilient, globally connected workforce capable of mitigating disaster risks for vulnerable populations. Part B, Case Studies and Global Practices, renumbered from original Part 4, includes Chapters 11-12, Chapter 11, High-Risk Regions, Design Innovations 11.1 Japan's Tsunami-Resistant Coastal Infrastructure, Key Innovations, Multi-Layered Defenses, Seawalls, Vertical Evacuation Towers, Smart Floodgates. Benefits, reduced casualties in post-2011 tsunamis, integration with early warning systems. Challenges, environmental impact of seawalls, high maintenance costs. Case study, Onagawa Town's elevated infrastructure and disaster resilient zoning. Integration, links to Chapter 18.3, Japan's Resilience Engineer Training, and Chapter 10.3, AI Monitoring. 11.2 New Zealand's seismic isolation in Christchurch rebuild, key innovations, base isolation, lead rubber bearings, for heritage and modern buildings. Benefits, minimized damage during the 2016 Kaikoura earthquake, rapid economic recovery. Challenges, high retrofitting costs for historic structures. Case study, Christchurch Art Gallery retrofit and the Cardboard Cathedral. Integration, connects to Chapter 8.1, Base Isolation Principles, and Chapter 16.2, Workshops on Isolation Systems. 11.3 Turkey's Failures and Reforms Post-2023 Kahramanmaraş Earthquakes, Key Lessons, Systemic Flaws in Construction Practices, Corruption in Code Enforcement. Reforms, stricter building codes, retrofit campaigns, and contractor accountability. Case study, Build Back Better initiative in Hawaii using modular housing. Integration, aligns with Chapter 13.2, Tax Incentives for Retrofits, and Chapter 12.2, Community Training in Nepal. Chapter 12, Urban Resilience and Community Preparedness 12.1 Earthquake Early Warning Systems, Mexico and California. Mexico's SASMEX delivered 60-second warnings during the 2017 Puebla earthquake. California's Shake Alert, integrated with BART for automated infrastructure shutdowns. Challenges, rural coverage gaps, Mexico, public awareness deficits, California. Integration, ties to Chapter 17.3, AI-driven alerts, and Chapter 13.3, UN Sendai Framework Collaboration. 12.2 Community Training and Building Code Enforcement in Nepal, NSET programs, train 50,000 plus masons in seismic-resistant techniques post-2015 Gorkha earthquake. Impact, retrofitted schools withstood the 2023 Dodi earthquake. Challenges, cultural resistance to abandoning traditional building methods. Integration, linked to Chapter 18.1, Skill Gaps in Developing Nations, and Chapter 9.1, FRP Retrofitting. 12.3 Resilient Infrastructure for Informal Settlements, Strategies, Low-Cost Retrofitting, Bamboo, Tire Foundations, Participatory Urban Planning. Case Studies, Haiti *, Build Changes 30,000 plus retrofitted homes post-2010 earthquake. Philippines *, Manila's People's Plans integrating informal settlers into disaster planning. Integration, connects to Chapter 14.2, Bio-Inspired Design, and Chapter 13.1, NERP's Equity Focus. Global Lessons Learned 1. Layered Defense, Japan's Hybrid Engineering Community Strategies. 2. Balancing Heritage and Safety, New Zealand's approach to preserving culture while upgrading resilience. 3. Equity in Resilience, Nepal and Haiti's community-led models for informal settlements. Future Outlook, Cross-Border Collaboration, Chile adopting Japan's tsunami barriers, Indonesia replicating Nepal's mason training. Tech Synergy, AI and IoT for real-time monitoring of coastal infrastructure, Japan, and informal settlements, Philippines. Integration with workforce development, case studies as training tools, Turkey's reforms and Nepal's NSET programs are used in Chapter 16.1, Internships, and Chapter 15.1, Certifications. Policy alignment, California's Shake Alert informs Chapter 13.1, NARP's public education mandates. Sustainability focus, Japan seawalls versus mangrove restoration trials in Indonesia, Chapter 14.1. Eco-friendly 3D printed components for informal settlements, Chapter 10.2. Conclusion, by dissecting successes, Japan, New Zealand, and failures, Turkey, this section underscores the importance of context-specific, community-engaged strategies. These global practices highlight how innovation, policy, and training converge to build seismic resilience in diverse urban and rural landscapes. Part 6, Codes, Policies, and Future Directions, renumbered from original Part V, includes Chapters 13-14, Chapter 13, Policy Frameworks for Seismic Safety 13.1 National Earthquake Hazard Reduction Program, NARP, Overview, a U.S. federal initiative coordinating FEMA, USGS, NIST, and NSF to advance seismic research, public education, and building codes. Impact, adoption of updated codes in high-risk states, e.g., California's post-Northridge reforms, and tools like HASIS for risk modeling. Challenges, funding instability and balancing retrofitting needs with rapid urbanization. Future, expanding NARP's scope to address climate-linked risks, e.g., liquefaction and AI-driven public alerts. 13.2 Incentivizing retrofitting, tax breaks and grants, key programs, California's Earthquake Brace and Bolt, offers grants for home retrofits, upgrading 20,000 plus homes since 2014. Japan's subsidies, financial support for retrofitting pre-1981 buildings. Equity gaps, limited accessibility for low-income households, proposed sliding scale incentives. Case study, Turkey's post-2023 earthquake grants for residential upgrades. 13.3 Global collaboration, UN Sendai Framework, goals, reduce disaster risks by 2030 through preparedness, resilient infrastructure, and international cooperation. Successes, Nepal's 2020 building code aligning with Sendai's standards. Chile's tsunami-resistant urban planning adopted by Indonesia. Challenges, disparities in funding and technical capacity between nations. Integration, NARP's risk models inform Sendai's global benchmarks. Tax incentives bridge policy and community-level retrofitting, e.g., San Francisco's Victorian upgrades. Chapter 14, Future Challenges and Innovations 14.1 Climate Change and Induced Seismicity, Risks, Geothermal/CCS projects, fluid injection triggering minor quakes, e.g., Basel, Switzerland. Glacial rebound, melting ice sheets reactivating faults in Alaska/Greenland. Solutions, AI-enhanced predictive models and international guidelines for safe energy projects. 14.2 Bio-inspired design, mimicking nature for resilience, innovations, bamboo-inspired flexibility, bendable structures in Vietnam. Self-healing concrete, bacteria-infused materials for crack repair. Challenges, scaling lab concepts, e.g., Caltech's seismic spider, to real-world use. 14.3 Quantum computing for seismic simulations, applications, fault modeling, high-resolution simulations of tectonic interactions. Risk optimization, efficient evacuation route planning. Barriers, current hardware limitations, error rates, qubit stability. Case study, IBM's quantum research on seismic wave propagation. Integration, bio-inspired designs leverage quantum simulations for optimization, e.g., route-like foundation systems. Climate policies must address induced seismicity from green technologies. Global and ethical considerations, sustainability, NERP's focus on marginalized communities, e.g., mobile home retrofits. Bio-inspired materials reducing life cycle environmental impacts. Equity, Sendai's push for land rights in informal settlements. Democratizing quantum tools via cloud platforms for developing nations. Future outlook, policy evolution, adapting codes like ASCE 7 and Eurocode 8 to integrate AI, biodesign, and climate resilience. Cross-sector synergy, tech firms partnering with governments on quantum seismic modeling. Architects collaborating with biologists on nature-inspired structures. Global metrics, Sendai framework tracking reductions in seismic mortality/economic loss by 2030. Conclusion, Part 6 underscores the dynamic interplay between established codes and emerging innovations. By evolving policies like NERP and the Sendai framework to address climate risks, bio-inspired solutions, and quantum advancements, the seismic engineering field can build adaptive, equitable, and future-ready resilience strategies. Appendices - Appendix E, Sample Industry Training Modules and Competency Checklists 1. Training Module, Seismic Retrofitting Fundamentals, Objective, train engineers/masons in basic retrofitting techniques, e.g., FRP wrapping, shear wall installation. Key topics, Seismology Basics, link to Chapter 1.1. Code Compliance, ASCE 41, FEMA P58. Hands-on FRP application. Duration, 40 hours, theory and field work. Competency Checklist, understands load path continuity. Demonstrates proper FRP layering. Passes written exam on ASCE 41 Tier 1 screening. 2 Training Module, AI-driven risk assessment, objective, upskill professionals in AI tools for seismic risk modeling. Key tools, OpenQuake, ASCE, MATLAB scripts. Case study, California's Shake Alert integration, link to Chapter 12.1. Checklist, generates fragility curves using AI algorithms. Interprets real-time sensor data for early warnings. 3 Competency Checklist Template Skill Proficiency Level Assessment Method Base Isolator Installation Advanced Field Observation Code Compliance Review Intermediate Written Exam Appendix F, Templates for Internship Agreements and Continuing Education Plans 1. Internship Agreement Template, Parties, University/Organization Name and Host Company. Objectives, apply seismic design principles, ASCE 7, to live projects. Develop skills in retrofitting soft-story buildings. Responsibilities, in turn, complete assigned tasks, e.g., ASCE risk modeling. Mentor, provide weekly feedback and safety training. Duration, start date to end date. Compensation, stipend of $X or academic credit. Confidentiality, non-disclosure of proprietary designs. Termination clause, conditions for early termination. 2 Continuing education plan template, professional, name, license/certification number. Goals, master performance-based design, link to Chapter 3. Complete FEMA ME course E190. Activities, attend ASCE workshop on base isolation, 8 CEUs. Enroll in Stanford's online seismic course. Timeline, Q1 2024 Q4 2025. Supervisor approval, signature/date. Appendix G, Directory of Certification Programs and Accreditation Bodies Organization Certifications Website Region CAIC Seismic Design Certification COC.org, https://www.caic.org, USA, California, EERI Seismic Risk Assessment Specialist ERI.org, https://www.erie.org, Global ICC Structural Engineering Certification ICCSafe.org, https://www.icsafe.org, USA/International NSAIS Structural Engineering, ASCE, license ncs.org, https://www.nsais.org, USAIAEE International Seismic Engineer IAEE.or.jp, https://www.iaee.or.jp, Global Note, verify renewal requirements and regional reciprocity. References Industry Reports 1. FEMA. 2022, Seismic Training Needs Assessment. Federal Emergency Management Agency. Link, https://www.fema.gov, 2. World Bank. 2021, Resilient Infrastructure Workforce. World Bank Group. Link, https://www.worldbank.org, Organizations 1. International Association for Earthquake Engineering, IAEE. IAEE.or.jp, https://www.iaee.or.jp, 2. Applied Technology Council, ATC. At council.org, https://www.atcouncil.org, Tools 1. NIST. 2023, Seismic Link, https://www.nist.gov, 2. ASCE. 2023, Body of Link, https://www.asce.org, Training Toolkit. National Institute of Knowledge for Civil Engineers. American Standards and Technology. Society of Civil Engineers. Note, for the most current standards and tools, consult the organization's official websites. Templates should be reviewed by legal professionals before implementation. This section equips readers with actionable resources to implement the book's strategies, from training masons in Nepal to certifying engineers in California.